we're going to use the basic idea of this limit definition of the derivative. This limit as h approaches 0 of the difference quotient to prove a bunch of rules for derivatives. And we're going to spend a lot of time this whole week proving a lot of rules for derivatives so that we can just have them memorized and not have to do this limit every time. So first one we're going to do is find the derivative of a constant. And the rule for the derivative of a constant is that the derivative of a constant is always 100% of the time 0. Hold on one second here. Okay, sorry about that. So the first rule that we're going to talk about is the derivative of a constant. The derivative of a constant is 0. And so we should think about this as a function is like y equals some number, 7, let's say. Well, f of x plus h, when I have my function f of x equals 7, if I plug in x plus h for every x, what do I still have? I still have that constant, right? I still have 7. And f of x is 7, so this becomes 7 minus 7, or just 0, over h. The limit as h approaches 0. And we can simplify 0 over h into the limit as h approaches 0, which is 0, which is 0. Does that make sense? Why the derivative of a constant should be 0?
Is that notation at the top, the d over dx? Does that just mean derivative or anything else?
Yeah, that means derivative. Sorry, I forgot that I should probably mention that. So d dx, this notation here means the derivative of our function c with respect to x. And we're going to talk more about this, like what with respect to x means. But our functions will generally be in terms of x. And so generally what we'll be doing is we'll be taking the derivative with respect to x, meaning x is our variable. Sometimes we'll be taking the, sometimes we'll be taking the derivative of something that's not an x, and we'll be doing it with respect to x. That's going to get more complicated. We'll deal with that later. But for now, we're going to take all of our derivatives with respect to whatever variable we have there. So somebody had a question. What was your question?
Yeah, sorry about that. So if there's a test question or something that asks us just for the derivative, is that what we would put? We'd put d over dx of the function equals, and then our solution.
Yep, so long as the variable that we're using is x. Yep, that's exactly what we do. Yep.
Cool.
So if I asked you what's the derivative of 1,000, you would say
0.
Exactly. If I say what's the derivative of pi, you would say 0. Derivative of 834/15, the answer should be 0. The derivative of any constant is always 0. And yesterday we talked about the fact that the derivative is the slope of the tangent line, right? Remember when we talked about that? Hopefully. Yes, didn't we talk about that yesterday?
Yes.
Oh, good. All right. So here's my function, my constant function, y equals a constant, y equals 7, let's say. Well, any line that we try to draw tangent to this is going to be horizontal, right? And what's the slope of a horizontal line?
0.
0. And so the derivative of this horizontal line has to be 0 because the slope of that line is 0. So it all sort of interconnects there. Does that make sense?
Yeah.
when you were doing part of like the steps, my Zoom cut out. So I missed the part where why is it like 0 and not indeterminate, like algebraically?
Right, so it is at this point where we have the limit is h approaches 0 of 0 over h. That's still indeterminate. Okay? But 0 divided by anything is 0. So we can rewrite it as limit as h approaches 0, 0. The reason we can do that is because h is approaching 0. Technically, h isn't actually 0. So this is 0 divided by anything that is not 0, actually. Does that make sense? Does that help?
Yes.
Okay, cool. Awesome. So, first rule, derivative of a constant is 0. Everybody good with that one? Or any other questions on that? Cool. All right. It gets exponentially more complicated from here, obviously. So, all of this mess that's right here, don't even worry about it yet, okay? Don't even worry about where that comes from. I'll explain it in a second. So what we're going to do is we're going to try to find the derivative of any x to a power. So x to the n power. So x to the third, or x to the first power, or x to the 1,000th power. And the rule that we're going to be proving here is called the power rule because it's x to a power. So what we should do is we should write this out in the limit notation. So anytime we're asked to find a derivative and we don't have a rule for it, which we don't have a rule yet for the power rule, we want to do it as a limit first. So the limit is h approaches 0 of x plus h to the n minus x to the n over h. This is just our difference quotient for this function x to the n, right? X plus h to the n minus x to the n all over h. Everybody good with this piece as the limit as h approaches 0 of that difference quotient?
Yep.
Yep.
Okay, cool. Now comes the complicated, more difficult part of it here. All of this is the binomial theorem expansion of x plus h to the n. You don't need to specifically know all that notation. I wrote out some of it. Note that there's these dot, dot, dots in here. So this is like using Pascal's triangle. This is the 1, and then the next term in Pascal's triangle is the n, and then the n times n minus 1 over 2 factorial is the next term in Pascal's triangle, and n times n minus 1 times n minus 2 over 3 factorial. That's how you derive those numbers in Pascal's triangle. So those are the coefficients, and then your powers are all dropping by 1, and the h powers are going up by 1. That's just the binomial theorem expansion. So hopefully you can take a leap of faith with me and assume that as a calculus teacher, I know what the expansion of the binomial theorem is, and that's what it is. Everybody okay with that?
Do we have to know this?
You do not need to know that specifically. You should be able to use the binomial theorem to expand out something like a plus b to the third or fourth power, but nothing crazy like this. I'm not going to have you write out the standard form for a plus b to the n. Good or no?
Good.
Okay. So you're going to take this leap of faith that I've written this out correctly, which I promise you I have. So that's our x plus h to the n, and then we have minus x to the n, right? All over h. So just like with all of the other limits as h approaches 0 of polynomials, because, I mean, that's what this is, right? X plus h to the n is really just a polynomial once we expand it all out. What happens? All of the terms that didn't have h's in them should do what?
Cancel out.
They should cancel out. And does that happen here?
Yes.
X to the n and minus x to the n, right? Those cancel out. So I can ignore those. And we're then left with a limit as h approaches 0 of n x to the n minus 1 times h plus, and I'm not going to bother to write out all of this stuff, but all of this stuff stays the same, right? Plus our h to the n at the end. Everybody good there? all over h. And what do you notice then about every term in the numerator? Every term in the numerator still has what?
H
An
attached
H.
to it.
Still has an h attached to it. We've got the h in the denominator, so we can then rewrite this as the limit as h approaches 0 of, well, divide out the h from each of those terms. So we've got nx to the n minus 1 plus, I'll write this one this time, n times n minus 1 over 2 times x to the n minus 2 times h, and so on, a bunch of terms with h's. And then this h to the n at the end should become h to the n minus 1. Everybody good there? Or no? So I divided the h out of the first term, I divided the h out of the second term, I divided the h out of every term, so that each of these went down by a power of 1.
Oh,
Good
so
or no?
since the last one is h to the n, you just like show that it's going down 1 by minus 1.
Yeah, exactly, right? So
Okay.
like, you know, if I have h to the n, my h's and my n's look unfortunately similar. But h to the n over h to the first, right? Well, if this is, you know, same base and you're dividing, then it's just h to the n minus 1, right? You subtract the
Okay, yeah.
exponents. Yeah. Cool. So now as h approaches 0, what is n times x to the n minus 1? It should stay as n times x to the n minus 1, right? And what about a big term here that's multiplied by h? As h goes to 0, this should be 0. And all of
0.
these should be 0. And this last one should be 0. And so all we end up with is just this n times x to the n minus 1. And that is the power rule. And the power rule says if I take the derivative of x to the n, the answer I get is n times x to the n minus 1. End of story. Pretty easy, hopefully. Okay. Any questions on how we got that? And then we're going to use it a bunch of times and make sure we know, because this is the rule that you're going to end up using more than any other rule for derivatives. So we're going to make sure we see how it works.
Are we gonna have to know how to prove this rule?
No, we will not have to prove any of the rules, especially this year. Especially this year, I'm not going to ask you to derive any of this stuff on a test or anything like that. Just be able to use the rules. But I still, I still want to be able to show you guys where things come from. So and normally I do even more like proofs of things as we go through, but we'll do less this year because we're crunched for time and it's harder on video than it is in person. But yeah, you don't need to be able to prove them. Okay, so let's take a look at x to the 7th power. And so this f prime of x, we see this notation. This also means the derivative of. So if we have f of x, the derivative of that is f prime of x. If we have a function y, the derivative of that is y prime, right? So these are just other ways to write out notations for derivatives. And we're going to see a lot of them as we go through this year. So if we have f of x equals x to the 7th, and we want to find f prime of x should be found just using this rule. The rule says x to the n becomes n, so we'll pull the 7 out. 7 x to the 7 minus 1, or 6. Any questions on that? Everybody good with that? All right, cool. That's the power rule. Very simple, very straightforward. So if I have y equals x to the 4th, what does y prime equal?
4x to the 3rd.
4x to the 4 minus 1, 4x to the 3rd. Easy enough?
Yep.
All right, and what about this last one? The derivative of x to the 50th should be just 50
50x. to the 49.
X to the 49. Okay. Simple, straightforward, power rule. Easy enough?
Yep.
Cool. Way easier, way better than trying to write out x plus h to the 50th power minus x to the 50th divided by h and expanding it all out and simplifying. It's much easier. Would you all agree with that?
Yep.
Cool.
Definitely.
Yeah, much, much easier. All right, so the next rule that we're going to talk about is this rule about a constant. And we can pull a constant out from our derivative. So we're saying u is a function that we can take the derivative of. So often we'll use u as a substitution for some other function. But we could also write this as like, just c times f of x if we wanted to. But we can take that constant out of the derivative and then multiply it back in at the end. And the reason we can do that is, what is a derivative? A derivative is just a limit, isn't it? Do you guys agree that a derivative is just a limit? So if the derivative has a constant stuck within it, right, in both parts of the numerator, we can take that constant and pull it to the front of the limit, evaluate the limit, which is our derivative, and then multiply the derivative by the constant. Does that make sense to everybody?
Yeah.
Okay.
So on the top, when it says c of d times u over d of x, is that d of u just the derivative of u with respect to x, or?
That's exactly what that is. That's the derivative of the function u with respect to x. That's exactly what that is.
Okay.
So you'll see us, you'll see me write du dx for the derivative of u with respect to x, dy dx, df dx sometimes. Usually it's like dy dx, or du dx. But if I say theta equals x to the 4th, then I would say d theta dx is equal to 4x cubed. The derivative of the function theta with respect to x, so my variable is x, is just the derivative. The derivative of x to the 4th is 4x cubed. Does that make sense? Does that help with the notation a little bit?
Yeah.
Doesn't matter what variable I use here. I could say, I could put any Greek letter, any letter from the alphabet. I could, put anything I wanted there and use that notation. Okay, cool. So if I want to find the derivative with respect to x of 5x to the 4th, this should be the same as 5 times the derivative with respect to x of x to the 4th, based on this rule with the constant. Would you guys agree with that?
Yes.
Everybody okay with that? That's exactly what we've got here, right? Is we've got the constant times the function, so we pull the constant outside. Now we'll find the derivative. Derivative of x to the 4th is 4x cubed multiplied by the 5, and you end up with your final result of 20x cubed. You don't need to write this step every time. Just recognize that what happens is this power gets multiplied by the coefficient that's out front, and then that becomes our new coefficient, right? The 4 times the 5 gives us 20. We drop the exponent down from 4 to 3. So this notation right here with the capital D with the subscript x is just another notation for the derivative of this function with respect to x. The derivative with respect to x of 11x to the 8th should be what? We should multiply this power by our coefficient to get what?
88, or 88 times x to the 7th.
88 and then x to the 7th, because we dropped that power down by 1. Everybody good with that?
Yep.
Any issues or questions on extending the power rule there with a coefficient out in front?
I have a quick question. This is
Yeah.
about notation again. Is there
Okay.
one uniform notation that they use on the AP test, or are like any of these fair game?
You will see any and all of them.
That's annoying.
Yes, it is, but that's okay. Some of them are better for certain situations, and we'll see that as we kind of move throughout the year. You'll kind of get used to when you'll see certain notations in certain situations, but yeah, they could all show up anywhere. All right. So we have a sum and difference rule for derivatives, and hopefully this should make sense pretty intuitively also. If I have the derivative of a function plus or minus another function, so like x to the 5th plus 3x cubed, let's say, like we have below, I can do each derivative separately. So I can do the derivative of my u function plus the derivative of my v function. And here we have du dx plus dv dx. The reason why that works is, once again, what are these derivatives? These derivatives are just limits, and we already said that if I have a limit of one function plus another function, I can separate that out into two separate limits, right? And so basically all of these rules that applied with limits should still apply with derivatives, because derivatives are just limits that we're doing in a shorthand notation. Does that make sense?
Yeah.
Okay, so the derivative of, of f of x equals x to the 5th plus 3x cubed should be f prime of x equals, and what's the derivative of x to the 5th? Using the power rule, it should be
5x to the x to the 4th.
5x to the 4th, and using the power rule with the constant in front of it on the second part of it should be
9x squared.
9x squared, right? These derivatives should be, I hope, pretty straightforward. It's just some simple arithmetic, right? Once you get the hang of the rules and what to do with them. So now we want to find dy dx for this other one. I got a bunch of things being multiplied together. That's fine. 4x to the 10th should turn into what?
40x
to the 9th.
40x to the 9th, good. And what about 1/2 x to the 6th? That should turn into
3x to the 5th.
3x to the 5th, right? 6 times a half gives you the 3x to the 5th. Next term, 5x to the 5th should turn into 25x to the 4th. And what about their minus 2x term?
Would it just be -2?
It's just going to be -2, right? If we think about it this way, minus 2x to the 1st should become -2, because you multiply the 1 by the -2, x to the 0, and x to the 0 is just 1. So if you're going from just an x, the derivative of something times x is just that constant that's in front of it. And it goes away. And then the derivative of the 3 should be
0.
0. Don't need to bother to write that. dy dx is 40x to the 9th plus 3x to the 5th plus 25x to the 4th minus 2. Good or no?
Yeah.
All right. Any issues so far? It's going to get more complicated as we go, so I'm going to make sure we're all good so far.
Yep.
All right, cool. The power rule is able to be extended, not just everything we've done so far was just like, natural number exponents on it, but it can be extended to any real number. So that means negative numbers, it means fractional exponents, it means irrational exponents even. Like if I have x to the e, right? E is just an irrational number. If I have x to the e, I can still use this same rule to find the derivative of that. So real quickly, let's go through and see if we can apply this using some slightly more complicated ones. So the derivative of x to the -1 should be what? We take this exponent and multiply it by the coefficient. Well, we have no coefficient now other than just a 1, so that should become -1 x to the what power?
-2.
-2. Everybody good with that being -1 x to the -2, or just -x to the -2?
Yep.
Okay, and if we wanted to rewrite this, now I'm fine with you leaving your answers in negative exponents. So is the AP test. But there are some situations when we're applying some of the material where you're going to need to rewrite this as -1 over x squared in order to help you solve something. So make sure that you can convert your negative exponents into positive exponents into the denominator. Everybody good there?
Yep.
All right. So what about the derivative of x to the negative fourth? What should that become?
Negative 4x to the negative fifth.
Yep, negative 4x to the negative fifth. Or we could rewrite that as negative 4 over x to the fifth. Everybody good with that both ways there?
Yep.
Cool. What about x to the 3/2? What should we get for that one?
Would it be like 3/2 x to the half?
3/2 x to the 1/2. That is exactly what it would be. What is x to the 1/2 the same as? That's just a, how else can we write that?
Square root.
Square root of x.
Square root.
So if we want to, now leaving it as x to the 1/2, fractional exponent is fine. I have no problem with that. But sometimes it might be more convenient for you, easier to look at if you rewrite it this way for some context of the problem. So just be able to, switch your rational exponents into roots as well. And what about the derivative of the square root of x? First, we'll want to write that as the derivative of x to what power?
1/2.
X to the 1/2, exactly. And so when we do that, we should end up with 1/2 x to the
Negative 1/2.
negative 1/2. And a negative fractional exponent is fine. I have no problem with that. But make sure you can rewrite it as 1 over 2 root x. Right? That's what that should become, right? 1 over 2 root x. The x to the negative 1/2 drops to the denominator, become positive 1/2, and then we can write it as a square root. Everybody good or no?
Good.
All right. This is a rule that you'll probably just want to memorize because the derivative of the square root of x comes up very, very often. So memorize that one. I'm going to give you guys a sheet of all the derivatives you should eventually have memorized. I'm going to put it up in the Google Drive. But this is one of the ones on the sheet that will pop up often, and you will want it memorized just to make your life a lot easier, especially when we throw things in there like, the square root of something like sine of 4 theta or something like that, and you have to take the derivative of that. It'll be a lot easier if you just know the basic derivative of square root of x to begin with. All right. Why don't you guys see if you can do these two on your own, and then we'll go through them real quick afterwards and make sure you guys got them right. Sound good?
Okay.
All right, give those two a try. It shouldn't take more than a minute or two. All right, how'd that first one go? Any issues with that? The x to the 2/3 should become what?
2/3 x to the negative third.
2/3 x to the negative 1/3, and then the 4x to the negative 3 should become minus
12x to the negative fourth.
12x to the negative 4. Good? Everybody good with that?
Yeah.
Okay. If you want to rewrite this as 2 over 3 cube roots of x minus 12 over x to the fourth, that's fine. I'm just going to leave these like this for now. But make sure you know how to do that. Make sure that's a concept you can use with the negative exponents and dropping them in your fractional exponents into roots. Because like I said before, sometimes you're going to need to for the context of the problem. But right now, not necessary. All right, what about this second one here? F prime of x is, what did the first term become?
X to the negative 4/5 power.
X to the negative 4/5, good. Next term became what?
10.
10x to the negative 6, and then the last term should have been 6x cubed. You guys agree?
Yeah.
Awesome. Everybody doing okay with those? Any issues with those? So I'm going to make it slightly more irritating next. Couple more. All right. Last two of these that we're going to do, and then we're going to kind of keep pressing forward with some other stuff here. Kind of apply this a little bit. So give those two a try also. All right, so any luck with those? We feel okay about those, or you guys need another minute? No response. You're good? Okay, so let's do this first one here. Root x, so that's one you're going to just have memorized, right? That should be 1 over 2 root x. Or if you wrote it as 1/2 x to the negative 1/2, that's fine. This second term was 5x to what power originally? If we rewrote this.
3/4.
Exactly, 3/4. So that should have turned into 15/4 x to the negative 1/4. Everybody good with that?
Yeah.
Okay, and then this 10th root of x is x to the 1/10, so that should be minus 1/10 x to the negative 9/10. Everybody good there?
Yeah.
All right, cool. Now what about the 1 over root x? 1 over root x should have been, that's x to the negative 1/2 to start with, right? So when we take the derivative, it should be negative 1/2 x to the negative 3/2, and then the second term was just an easy one, 15 x squared. Any issues with that? All right, cool. So now here is the 4 most common notations that we're going to see. And these are starting with the initial function f of x, let's say, or y. This term here is the first derivative. Okay? That's what we've been dealing with. So f prime, y prime, dy dx, the derivative of y with respect to x. That's what these all mean. These are the four more common notations that we'll see. Then we can take a second derivative, okay, or a third derivative, or a fourth derivative, all the way up to whatever derivative we want, the nth derivative of f. Okay. So same here, y prime, y double prime, y triple prime, the fourth derivative of y, the nth derivative of y. Okay. Y dy dx, so the derivative of y with respect to x, or this, which we read as the second derivative of y with respect to x, the third derivative of y with respect to x, and so on. Okay. So these are the notations you're going to want to know and get used to. And we're going to start now taking higher order derivatives, is what we call it. So rather than just a first derivative, we're going to take the derivative of the derivative, or the second derivative, or the derivative of that, which is the third derivative. The convenient thing is all the rules still apply as we go through. The derivative of the derivative, or the second derivative, is just a derivative. So it's not anything more complicated. It just means you got to do it twice to get to the second derivative, or 100 times to get to the 100th derivative. Okay. Everybody good there? This will be up in the notes, so if you want to refer back to it, that's fine later on. So let's find the first four derivatives of 2x to the 5th power. So first off, what should f prime of x be?
Ten x to the 4th.
10x to the 4th, good. So now our second derivative of x should just be the derivative of this, which should be
40x to the 3rd.
40x cubed, exactly. Our third derivative, f triple prime of x, would just be 120x squared. And our fourth derivative of x should be what?
240x.
240x.
240x, great. Pretty straightforward, easy. We're just using the power rule straight through. There are a lot of good reasons for us to take the first and the second derivatives of functions. We will spend most of our time dealing with those, but occasionally we'll look at higher orders than the second derivative. So just be aware of the notation. But most of what we'll do in this class revolves around first and second derivatives when we're talking about derivatives.
I have a
Alright.
quick question.
Yes.
So if a derivative is the slope of the tangent line, what are all these higher derivatives like represent?
Well,
If they
so
represent anything.
I mean, the first derivative is the slope of the tangent line. The second derivative is the slope of the tangent to that line, which is just the same as that same slope. But when we go into applications of this, they're going to mean lots of different things. They mean a lot of different things on the graphs. So for example, the second derivative tells you concavity of the function. And if we're talking about motion problems, like in physics, the original function is a position function. And then the first derivative ends up being a velocity function. The second derivative ends up being an acceleration function, and so on. There's things beyond acceleration. Does that help answer your question or not?
Yeah, it does. It's just
Okay, yeah, and then we're going to see uses for them rather than just the slope of the tangent line, especially when we're talking about how the graphs of the functions behave. So, yeah, the higher order ones in this class, they don't do a whole lot for us usually, but sometimes we'll have to deal with them. All right, so let's do this one. Let's find the first four derivatives of 4x to the 3/2. So once again, these should just be using the power rule. So what's the derivative of 4x to the 3/2?
6x to the 1/2.
6x to the 1/2. And again, if you want to write that as to the 1/2 power, or you want to write it as root x, then that's fine also. What about f double prime of x?
3x to the negative 1/2.
Good? Everybody good with that? Our third derivative should be
-3/2 x to the -3/2 power.
good. And our fourth derivative should be what?
9/4 x to the -5/2 power halves.
-5/2, -5/2. Or, you know, you could do 9/4 square roots of x to the 5th. If you wanted to write it that way, that would be fine too. But this is good too. Any questions or issues with that? Hopefully this should seem really easy so far. Let's do another one. You guys do these ones and then I'm just gonna quickly write them out and make sure you guys got them right. So take a minute or two, and probably a minute, and write those 4 derivatives. Everybody got those 4 done? Yes. All right, so the first one was -6x to the -3. Was 18x to the -4. Next one, -72x to the -5. And the last one was 360x to the -6. Anybody have any discrepancies there? Any questions on that?
Nope.
All right, cool. Last one of these I think I got up here for you guys to do. First 4 derivatives of 50x to the 2nd power. So f prime of x should be what?
100x.
100x. Our second derivative should be what?
100.
100.
Just 100, right? Our third derivative should be
0.
0.
0.
And what about our fourth derivative then?
0.
Still 0, right? 0 is still a constant, so the derivative of 0 is 0. If I want to take a 5th, the 6th, the 7th, the 100th derivative of this, we know that it's just going to continue to be 0 the rest of the time. Good? Or no?
Good.
All right. Cool. So let's do a couple of basic applications here now. Let's see if we can figure out if this function, x to the 4th minus 2x squared plus 1, has any horizontal tangent lines. So let's conceptually think about what that means. If the tangent line is going to be horizontal, what does that tell you about it?
Has a slope
Slope
of
is 0.
Right, it means that the slope is 0. The slope of the tangent line is 0. And the derivative represents the slope of the tangent line, right? So what we're really interested in here is, when does the derivative dy dx of this function equal 0? Does that make sense to everybody?
Yep.
Okay, so we should really easily be able to find the derivative of this. What does dy dx equal?
4x cubed minus 4x.
4x cubed minus 4x, exactly. And we want to know when does that equal 0. So we should be able to factor out the what?
4x.
Factor out the 4x, leaving you with x squared minus 1. Set equal to 0. And how do I solve that equation? Zero product property, right? Set 4x equal to 0. And the x squared minus 1 equal to 0. So it should have horizontal tangent lines when x is 0 and when x is positive or negative 1. We agree?
Yeah.
Cool. So let's take a look at the graph of this real quick. I'm going to pull up Desmos and share Desmos with you. We had what do we have? X to the 4th minus 2x squared plus 1, right?
You didn't switch to oh, never mind. There it is.
All right, so x to the 4th minus 2x squared plus 1. And we should note that at x equals negative 1, what does our graph have here?
A minimum.
It has a local minimum. We're going to talk more about that, but it has a minimum. Okay? And at x equals positive 1, it has the same. It has a minimum. And at x equals 0, it has a maximum, right? And these are places where our derivative is equal to 0, where our tangent lines are horrible, are horizontal. Is that good? That makes sense? We would see that if I put in y equals 1, there's your horizontal tangent line right there. And y equals 0, horizontal tangent line there.
So when the derivative equals 0, that's when like the graph is turning points.
That's exactly correct. Yep.
Okay.
And we're going to spend a lot of time talking about that and looking at some far more complicated functions in this one, and finding these places where it has those turning points, or these, we call them local maxes or local mins. That's going to be a big part of when we do the applications of the derivative. But I just want to sort of introduce the idea now and see a little something we can do with this derivative. Any other questions on that? Are we good?
Wait, so the answer was, one of the answers was x equals plus or minus 1, right?
Right, so at x equals, so no, we're talking about x values, right? So at x equals 1, we've got 1, and at x equals negative 1.
Yeah, I see that now.
Cool. Any other questions on that?
Can you go back to the slide?
Yeah.
Would you ever want to write your answer as like the tangent line, so y equals 0 or y equals 1 or y equals negative 1?
Yeah, definitely we will want to. Not in this case, just because I asked where do they occur. So if I ask where do they occur at x equals 0 and x equals positive or negative 1. But yeah, in order to figure out what they actually are, we'll take these values and plug them in up here. So if you plug in 0, you get y equals 1, right? And that's the tangent line that we had at x equals 0. And same with if you plug in 1, that's 1 minus 2 plus 1, you get 0. Same with negative 1. And so that's why at 1 and at negative 1, the tangent line was y equals 0. And at x equals 0, that's why it was y equals 1. Does that make sense?
Yeah.
Cool. Any other questions or anything you guys are wondering about that, or does that all make sense? All right. Okay, let's do one more just like that, and then that's going to be it for today. You guys want to try this one on your own?
Sure.
Yeah.
All right, I'll give you guys maybe 3 or 4 minutes. Try and figure out if it has any horizontal tangent lines and where they occur, and then we'll go through it and help you out if you have any questions. All right. Did everybody finish that up, or you guys still need another minute or two?
Good.
Good? Okay.
Good.
All right, so what is y prime or dy dx? It should equal what?
squared
3x squared
minus
minus 4.
Oh yeah.
We got x squared, right? 1/3 times 3 is just x squared
Mm.
minus
Oh,
4.
yeah.
And we're interested in horizontal tangent lines, which means when does this derivative equal 0? X squared minus 4 equals 0 when x is plus or minus 2. That should be our answer. Did anybody by chance go in and figure out what those horizontal tangent lines were?
Y equals -5/3 and 11/3.
11/3 and -5/3.
Yeah.
All right, I'm gonna hope that you're right. We're gonna see if you're right. Let's look at the graph. I haven't actually done that. So on Desmos, our original graph was what, 1/3 x cubed minus 4x plus, what was it, plus
9.
9? Okay, cool. And so we can see that, yeah, at x equals 2, we clearly have this local minimum, right? And up here, we've got our maximum. I think those values you got out there might not have been right, though. So let's take a look and see what happened there. 11/3, was that one right? Okay, so 11/3 looks good. That's what you got when you plugged in 2. But -5/3 doesn't look like that's going to work, right? Because that's way down here, and we need it to be up here. So we must have made a little arithmetic error there. Let's take a look at the one for when we plugged in -2. So if we plug in -2, -2 cubed should be -8. So this should be -8/3, and then +8 plus 9. So that should have been 17 minus 8/3, which, what does that come out to be? 43/3? Does that sound right?
Yeah.
You know what?
So let's go in here.
Sit up and pay attention.
So 43/3 looks like that's where it touches our axis, or it touches our function. Any questions or issues on that? We kind of see how that all works. Everybody feel okay about that?
Yeah.
Yep.
No issues, no problems, no nothing? Everybody's good?